So we've looked at using logistic regression for classifying data into different pieces, specifically two pieces, what we call binary classification. Like we said, we will generalize this to multi-class logistic regression pretty soon, but today we'll still do binary classification, but with more sophisticated data or more complex data, if you will, more high-dimensional data. And the data set we are going to look at is called MNIST database, which stands for Modified NIST Database. NIST stands for National Institute of Standards and Technology, which is a federal agency. And this data set consists of these handwritten numbers, essentially. Each image contains one handwritten number, and there's 60,000 images or something, or total of 70,000 images. In any case, so that's the data set we are going to use. As you can look at the history of this data set and its influence in the machine learning literature and pedagogy. Yes. So these folks are the people that created the MNIST database, but like we said, it's a modification of what's called the NIST database, which is created by some other bunch of people at NIST. Okay, so you can download the data from this website, but for you guys, I guess I've just uploaded the data onto Carbon as a MAT file, so you can use that. Okay, so let's do that. So I think that's all I wanted to show here. Actually, let me just go here. If you scroll down and click on here, lists of data sets for machine learning research, there's a large list of data sets, I guess, many of which are freely available. Probably most of these are freely available. And on the next homework, I will ask you to explore some of these data sets. Okay, so now let's look at the MNIST data set. So I'm going to divide this video into two pieces. The first video is just to load the MNIST database data set and then sort of plot the images so that we can get some intuition about what the data looks like and so on. And then the next video, we will actually do logistic regression to build classifiers to say, identify that a number is 5 versus not a 5 or something. Okay, so here's the mat file, mnist.mat. We can load it. Let me just load it. Okay, as soon as you load, you get 4 variables: train X, train Y, test X, test Y. So these two things belong to the training set. These two things belong to the test set. They've already divided that into a training set and a test set for you. So the idea would be to train a classifier on this thing and then see how accurate is it on the test set. Okay. Now, of course, the X variable is the input, which is the image. The Y variable is the output, which is what is the number that the image contains. Okay. So if you say train X here, I'm just going to press enter, and just looks like that. Horrible. Okay. I just control C out. But notice that it is 60,000 rows, 785 columns. Okay, 60,000 rows, 784 columns. 784, not 785. So there are 60,000 images, it turns out. And then if you go train Y, this is train Y. It's given as a column vector, but doesn't matter. Sorry, a row vector. And basically says the 60,000th image is an 8. It says if you go more on and then say train Y, it'll show this vector to you page by page. It says the first image is a 5, this next image is a 4, next image 0, next image is a 4, next image is a 1, next image is a 9, and so on. Okay, That's what this data contains. And then train X, the first row is the first image, the second row is the second image, and so on. So each row is a separate image. Okay. So let me actually show you the MATLAB program that will take the row, ith row, which is the ith image, and then convert it into an image and then plot it. Okay. So let's just walk through that. Okay. So that's just clearing everything. This is just loading something. If you notice, oops, if you notice 784, the number of columns um, for this data set, that's the number of pixels in the data. Okay, so if you go square root of 784, that's 28. So it's actually an image which is 28 by 28. It's a square image, 28 pixels by 28 pixels, but stretched out into a single, rather than give you the information for an image as a matrix, 28 by 28 matrix, they're just giving it to you as a 784 column, one row, row vector. Okay, so anyway, so here we're loading it. I'm just saying this is the length of train Y. Maybe we don't want to say length. Let's say we want to say size of, I guess length is fine, because train Y is just a row vector. Okay, so there are 60,000 training data points, and then 10,000 testing data points, and we can say this is square root of 784. Doesn't matter. Okay, we already know that it's 28 by 28. Okay, so now what we're going to do, we're just going to display each image. Okay, so I'm just going to comment this out and say I index. Okay, so right now I'm going to display the first 5 images. I'm saying I index goes from 1 to 5. I displayed as I index. M now is a variable. I'm saying it's train X. I displayed comma colon. So it'll pull out basically one row, the ith row. And then there's a command in MATLAB called reshape, which can reshape one matrix into another matrix. So what we're going to do here is we're reshaping a 1 times 784 matrix into a 28 by 28 matrix. Okay, so I'm going to put a pause here and run this until here. And that I seem to have turned more on, so just showing me page by page. So I'm going to Control C out here and go more off so that we don't waste time. Okay, so M is now a 28 by 28 matrix. So just showing you that. M initially was a 1 times 784 matrix because you just pulled out the ith row, and then we've reshaped it into a 28 by 28 matrix. For this reshape command, of course, the size of this matrix and the size you give here should be compatible, right? So the number of elements here should be the product of these two numbers. Otherwise, it will not be able to reshape this into this. Okay, so now we've reshaped it into a 28 by 28 matrix. And then there's a command called IAmShow, which will just show you what the image is. So let me just actually do this in the command line. You can just go IAmShow of M. Okay, so that's what that looks like. Okay, so that's the first number. The first number is a 5, or so it looks to us, to our eyes. So we can check if that's a 5 actually. If trine y of 1 is a 5, okay? So that looks like a 5. And so on and so forth. We can plot, um, we can run that loop. Let me just run that loop. Okay, so it's just plotting the first 5 numbers. And then I'm also having this text display what MNIST thinks this number is. I'm showing you the image, but also saying, using basically your train y, the first 5 elements of train y are 5, 0, 4, 1, 9. So let's see if that works again. 5, 0, 4, 1, 9. Okay, so we just plotted the first 5 numbers. The earlier version of the code was plotting randomly selected numbers. So I index equals 1 to 5. So we're going to plot 5 images, but then the image that I want to display, I randomly sample from 60,000, basically. Okay, I randomly sample one number from 1 to 60,000. That's what this does, and then try to plot that. So let me just run that now. This is some number it selected, I guess, from the 60,000 images. Okay. Okay, so now we are able to plot it, plot an image. Um, Now we can try to get some intuition. So whenever you have a new data set, you want to do what's called descriptive statistics. You should do simple things with the data potentially to get some intuition about the data. Unless you have some very precise hypotheses you want to test with the data, then you should just, of course, test those hypotheses. Um, if you just don't have any hypotheses, if you just want to understand some data set, just plot things like mean, median, standard deviation, and just sort of get some intuition about it. Okay, so we have 60,000 images. Is there such a thing called a mean image? Okay, a mean, like these 60,000 images are numbers from 0 to 10, 0 to 9. Of course, there's a mean for the numbers, but if you take the image of each of those numbers, the 60,000 numbers, and then take the mean of those images, in other words, for each pixel, you compute the mean intensity of the pixel. Okay, so something I didn't quite say yet is what is this 28 by 28 matrix? So you can take a look at that. So M is this 28 by 28 matrix, and it's a lot of zeros, and then numbers which seem to be integers, right? You don't see any decimal points. And then if you notice, I guess the highest value it would have potentially is 255. Okay, it's actually numbers. Each number in M is a number between 0 and 255. 255 is actually 2 power 8 minus 1. Okay, that's 255. What does that mean? Yeah, this is what would be called an 8-bit image. An 8-bit image allows for 256 levels, and they use 0 to 255 as those 256 levels. So each pixel is represented by 8 binary digits, 8 bits, right? Binary digit is what's called a bit. So 8, 0 or 1 numbers. And if you have 8, 0 or 1 numbers, there are 2 power 8 combinations, and they map that to 0 to 255. So there are 250 levels. What do these levels mean? They mean level of grayscale. 255 corresponds to white, 0 corresponds to black, and something in between corresponds to a shade of gray between black and white. Okay. So each pixel has a grayscale value, an 8-bit grayscale value. So that's the interpretation of these numbers. So just to be clear, and then we have 60,000 such matrices. We can take the mean. So there's a command called mean. We can just go mean train equals. Okay, so if you take the mean of the training data set, which is this 60,000 by 784 matrix, you get a 1 by 784 matrix. So you just get one row. But notice that these numbers are not any longer integers because you're now taking the average of 60,000 integers. It need not be an integer. So I have this little program that I wrote, which basically reshapes this vector of 784 numbers, reshapes it into a 28 by 28 matrix, and then converts it into an 8-bit integer. Okay, so because these images, I am sure at least I think assumes that these are 8-bit integers. So and then use IM show. Okay, so let me just run this thing, and this is now going to plot, take the mean and then plot the mean of all the images, all the numbers. Okay, that's the mean of all the whole data set. Okay, it looks like a mess. It looks like none of the numbers. Um, Sort of looks like a 3. There's maybe an 8 there. It sort of looks like that because many of the numbers have this pattern. Like I guess 5 looks like that, 4 looks like that, 9 looks like that, 3 looks like that. Of course, 1 doesn't look like that. Um, so you sort of get this pattern that is a superposition of all these numbers, right? Okay, we can try the median if you want. I'm just going to change this and not change the title of this. Let's see what the median looks like. Oh, looks even more like a 3. Strange. Okay. Um, okay. So that's if you average over all the numbers. What if you just take images corresponding to a single number and then average it? Um, and this is what you get. Okay, so you can now think about whether this would be better or worse. Um, so let me just run this thing. It'll just loop through. So it's just going mean of train X, but then it's just using those rows that correspond to train Y equals I number, right? So when train Y equals 0, we take all those train X's which have the images and then take the mean of all those things. So that's this cryptic command, right? So this is basically selecting all those images, all those indices that correspond to images containing 0 or 1 or 2, and then you just take those rows and then find the mean and then image display. Let's see what that looks like. Looks much better. Okay, the average of all the zeros looks like a 0, 1, 2, and so on. Okay, so that's what that looks like. Um, the rest of the program, I'm going to have you explore this. It plots the median of the individual numbers, and I have an exercise here just for your own, I guess, exploration. And then we plot the mode of the individual images. You have to look up what the mode is and see if that makes sense. Um, and then you will see that we can convert grayscale into black and white, and then do all these things, and some things look better. Um, so Let me just show you the median. Let me just show one of these things, I guess. The median of 0 looks like that, pretty nice. The mode of 0 looks horrible. The mode after black and white thresholding looks pretty good. Um, oops, it's trying to plot all of them. And then let me just go here. The median of the individual numbers. We previously plotted the mean. The median, this is after black and white thresholding, I guess. Let me Control C now. Looks pretty good. And then we can plot the standard deviation, which is another quantity. Okay, it looks kind of interesting. The standard deviation of all the images then contain a 1 there, contain a 2, contain a 3. Notice that the standard deviation of all the 4 images or the 5 images and so on is brighter actually at the edges of the image itself, of the number itself. Why is that? Something for you to think about. And okay, so you can think about why that is the case. So how would you now build a classifier that how do you build a classifier that separates, given an image, how would you build a classifier that says what that image is? Okay, so we can use logistic regression, but based on the information that we sort of intuition that we got from this exploration, you can potentially think of simpler classifiers, right? So given that the mean image for 0 looks like sort of a 0, if you're given a new image, you can maybe try to find the distance between the new image, the new vector, and the vector corresponding to the mean 0, and see how far that is, and maybe use how far something is from the mean of that sort of image for a particular number as a criterion for maybe classifying, right? So that would be one way to classify. Maybe I'll make a homework problem in a future homework that makes you sort of think of new and weird classifiers based on sort of these simple statistics. But in the next video, we're going to do essentially logistic regression to classify these images.